Hi everyone, welcome back to chemistry. In this video, we're going to start study guide 3, which is all about chemical bonding. But in order to talk about chemical bonding, we need to talk about electrons a little more because they're very important for bonding. So before we talk about electrons, let's talk about electromagnetic radiation. So electromagnetic radiation has lots of different forms. So there's light, there's visible light, so colors of the rainbow, there's X-rays, UV rays. And we measure electromagnetic radiation electromagnetic radiation consists of energy particles that move as waves of energy. I was kind of jumping ahead there. So let me draw my wave here. So this would be a wave. And in this wave, we can measure from what's called peak to peak. So those peaks, the highest spots on that wave, and that's called a wavelength, the length of one wave. And then that's usually measured in nanometers. But it can be measured in different things as well. Different units, sorry. You can also measure from here to here, which would be, which is called trough, measure from trough to trough. That's the same, should be the same length as peak to peak. So you can measure peak to peak, trough to trough, but you shouldn't measure from peak to trough because that would just be half a wavelength. So you don't want to do that. You want to measure a full wavelength. And then the shorter your wavelength, right? The shorter the distance between those peaks, the higher energy radiation you have. Okay, so that would be higher energy wavelengths. And then the longer the distance between those peaks or troughs, the lower energy you have. Okay, so high energy versus low energy. Okay, so the distance between those peaks kind of determines how short the wavelengths are and or long, and then how high or low energy they are. Okay, so you might have seen this, the electromagnetic spectrum. As you're reading this from left to right, the energy is increasing. Okay, the energy of your wave. And from on the left here, you see radio waves. Those are, they have longer wavelengths, so they're lower in energy, longer wavelengths, lower in energy. And then gamma rays, X-rays, UV rays on the right there, those are shorter wavelengths. Sorry, I guess that should be, it looks kind of like one word. Let's scoot that over a bit. So shorter wavelengths, which are higher energy, like we said before, right? And we know that kind of instinctually because UV rays are really damaging to us, and they're very high energy rays, which is why we need sunscreen and sunglasses to protect our skin and our eyes from those high energy waves. All right, and then on in this tiny little region here, you can see visible light, and they kind of zoom in for us. So on the left there, that's red light. And on the right is violet light. So on the left, red light has a wavelength of around 700 nanometers, and violet light has a wavelength of around 400 nanometers. And I'm saying around or approximate because there are different kind of, it's a spectrum, right? So I would call any of those colors kind of red and stuff like that. And then you'll notice that blue light is kind of like right here, more towards the higher energy side of the spectrum. And that's why scientists often talk about your cell phones and devices giving off a lot of blue light and keeping you awake at night, because that blue light's higher energy. When your eyes look at it, it can mess with your circadian rhythm because you'll think, oh, it's like sunny outside, and can actually make it so you stay up later or you can't sleep as well. And then they even have blue light blocking glasses, which actually make it so that your eye is seeing less of that blue light. And you're not getting as much of that effect from the blue light that keeps you awake. Okay, so, excuse me, atomic spectrum. So when, actually, this, I like to like kind of think of a real world example. So I don't know if you've ever looked at a prism before, or maybe you've seen that Pink Floyd album cover that looks kind of like that. That's what that always makes me think of. But when light goes through a prism, the light is actually bent so that you can actually see the individual wavelengths of light for these different colors. You're seeing red, you're seeing green, you're seeing orange, you're seeing, you're seeing blue, green, orange, and red, whatever. You know what I mean? And the prism is bending that light so that you can see those individual colors. So when we heat elements, specific elements, and the light from that element passes through a slit and hits a prism, we can see that it creates that spectrum that we can see, and that spectrum is actually unique to each element, and it's called an atomic spectrum. And each element has its own atomic spectrum. It's a fingerprint for the element. So barium's is the one that's represented here, and you can see all these like distinct lines for the different kind of lines that are coming off that you're seeing with barium. So if you didn't know that this was barium and you saw the light spectrum in lab, and you looked at, they even have periodic tables that have every single light spectrum for those elements, and you compared them, you'd be able to determine that you have barium. So very cool. And you'll actually do a really fun lab with this in Gen Chem if you take it here at TCC in the future. No spoilers exactly, but it's fun. All right, so moving on to electron energy levels. So the lines in an atomic spectrum like that we just saw up there are associated with the changes in energies of the electrons. So in an atom, each electron has a specific energy, and that's known as its energy level. And we represent that energy level with what's called the principal quantum number. And that principal quantum number, we use the letter N to signify that or to represent that. Okay, so whenever you see N equals some number, just know that you're looking at the energy level of the electron. So N equals 1 is the energy level 1. N equals 2 is energy level 2. N equals 3 is energy level 3, and so on. And as electrons are getting farther and farther away from the nucleus, that value of N actually increases. And we'll talk about why that is in the future, but just something kind of to note for now. Then what we've also noticed about electrons is that the energy of an electron is what we call quantized. And what that means is that electrons can have only these specific energy values, okay? So I like to think of, I actually really like this analogy that the book gives about a bookcase and this is for the quantized nature of electrons. Okay, this is kind of representing that, or their energy levels. So looking at this bookcase, as we go up this way, the energy is increasing, right? So we said N equals 1 is energy level 1, N equals 2 is level 2, level 3, level 4, and so on, right? So each of those shelves represents a different energy level that is increasing with each, the higher you go. So at that first energy level, the N equals 1, our energy level is 1, and if we put electrons on that shelf, it's pretty easy to put them there, right? So if you're like putting books on your bookshelf, the lowest shelf is the easiest to populate with your books, or in this is electrons, right? Because you're not reaching up You're not expending as much energy. If you're trying to put a book in the second energy level or the second shelf, it does take a little more energy, right? You're lifting up your arm. That book is feeling a little bit heavier because it's higher from the ground and the force of gravity is acting on that book. So it takes a lot more energy to get a book on the second level than it does on the first. So if you're lazy like I am, you'll probably put your books on the first level first, or the first shelf first, and then you'll move on to the second if you must, and then the third if you must, and so on. Okay, so we always kind of fill from bottom to top. Okay. Lowest energy levels get filled with electrons first. And that'll make more sense what I mean when I say filled later. Okay, so, and then what's important to note is that an electron can only have the energy of one of the energy levels in an atom. So what do we mean by that? That's going back to this idea of it being quantized, the energy levels of the electron being quantized. And what that means is when I'm putting these books on the shelf, I'm putting them either on n equals 1 or n equals 2 or n equals 3 or n equals 4. What I'm not doing is putting a book on n equals 1.5. What happens if I try to put a book right there? Yeah, I can't do it. There's no shelf to hold the book there. I guess I could do it. It would just fall. But there's no shelf there, so I can't put a book on that shelf. So that's the same thing with electrons. They can either go in n equals 1 energy level, they can go in energy level 2, they can go in energy level 3. They can't go in 2.5 or 2.4, stuff like that. That's just not what we see in nature. What we notice is they go on these exact specific energy levels. Okay. Another way you could think of it that I've heard it described before is stair steps. So if you have a bunch of stair steps and this is n equals 1, this is n equals 2, this is n equals 3, you know, and so on. When you are, you know, walking on those stairs, and, you know, I'm going to try to make this look good. You can step on this step, right? You can step on this step. But what you can't do is step on a step that doesn't exist. Okay? You can only step on the stairs that actually exist. It's kind of bothering me that these that they're not colored in. So I'm going to color them in. Okay, anyway. So you can, electrons are the same way. They're not going to, they're quantized. Their energy levels are quantized. So they only populate those specific energy levels. All right, hope that makes sense. So changes in electron energy level. So electrons can actually move to a higher energy level by absorbing energy. So if we look at this staircase again, if we wanted to go from n equals 1 to n equals 2, we have to absorb some energy to get there. Okay? You can, but you have to absorb energy. Likewise, you can go straight from n equals 1 to n equals 3. You can do a big jump, right? I don't know if you did this when you were a kid, but when I was a kid especially, I used to like jump up the stairs and try to like jump up a bunch of stairs, and then my mom would be like, can you just take it one at a time? So anyways, you can do that. You can jump, but you have to absorb energy, enough energy to do that. Okay, if you're really tired and you didn't have any food that day, you're not going to be able to do that. Okay, so electrons can move to a higher energy level when they absorb energy, and when they fall back to a lower energy level, something called a photon is emitted. So when those electrons go back, right, when they go back from this higher level to a lower level, they actually emit something called a photon. And a photon is, you could think of it as a particle of light. And that's simplifying things a little bit, but for our purposes, it's good. Okay, so a photon, like a particle of light, like a photo or a photograph. Okay, so when electrons fall back to a lower energy level, light is emitted. And it turns out that the energy emitted or absorbed is equal to the differences between the two energy levels. Okay, so the energy that it takes to absorb, the energy required to jump from n equals 1 to n equals 2 is the same as the energy emitted when you go back down a level. Okay, but then it's just emitted as a photon. All right, so let's keep going here. So sublevels. It's actually the arrangement of electrons that determines the physical and chemical properties of an element. So electrons are really, really important. We ignore them when it comes to mass because they're very, very small, but in many other ways, they are the backbone of chemical bonding. So each energy level consists of one or more sublevels. So you've got your energy levels, which is like your n equals 1, your n equals 2, your n equals 3. Those are your energy levels, right? And then within those energy levels, there are sublevels. And the number of sublevels in an energy level is equal to the principal quantum number of that energy level. So what do I mean by that? So if you're in n equals 1, you have one sublevel. Okay, if you're in n equals 2, you have 2 sublevels. If you're in n equals 3, you have 3 sublevels. Okay, and these sublevels are identified as S, P, D, and F. That's their name, that's what they're called. I know, kind of weird. Lots of vocab stuff this video. But it's okay, we got it. Okay, sublevels are identified as S, P, D, and F. Okay, and the order of the sublevels in an energy level goes from lowest to highest energy. Okay, remember our bookcase analogy. We're lazy. We want to be at the lowest energy level. So we're going to populate from lowest to highest. We're only going to expend lots of energy if we really have to, but we'll expend a low amount if we can. Okay, so it goes from S. So S is lower energy than P, which is lower energy than D sublevel, which is lower energy than F sublevel. Okay. Okay, so here's kind of a good picture of it. So on the left there, you've got your energy levels, right? Your principal quantum, sorry, that makes it look like I'm pointing to sublevels. So on the left, you've got your energy levels, your principal quantum number, n, right? N equals 1, 2, 3, and 4. And it goes further than that. There's n equals 5, n equals 6, stuff like that. And then you've got your number of sublevels, which is, remember, equal to your principal quantum number. Okay, so n equals 1 has one sublevel. Then we've also got types of sublevels. Okay, so there's the number of sublevels, and then there's the type. So the type is given by those S, P, D, and F. So if you're in energy level 1, you have one sublevel, and the type of that sublevel is S. And we'll talk about what S kind of looks like in a little bit here. Okay, if you're in energy level 2, you've got 2 sublevels, and those are your S and your P. You've got your S sublevel and your P sublevel. Those are your 2 sublevels. If you're in n equals 3, you've got your S sublevel, you've got your P sublevel, and you've got your D sublevel. Okay, if you're in n equals 4, you've also got all of those things plus your F sublevel. Okay. Okay, so what the heck is the S sublevel, or the P, or the D, or the F? So the big idea with, remember we said that electrons are really, really important. So scientists want to know kind of where we can find those electrons in an atom at any given time. But we can't because they're so, so tiny. It's really hard to know, there's no way of knowing the exact location of an electron in an atom. There is a way of knowing where it probably is. So we can describe the location of those electrons within an atom in terms of probability. So at any given moment, I think it's probably likely that we're going to find an electron in somewhere in this region. Your book kind of talks about the orbital. We call that location or that region an orbital. Okay, so orbitals are a three-dimensional volume in which electrons have the highest probability of being found. So your book talks about the orbital in terms of like an analogy of think about when you're sitting in the chemistry classroom. When you're sitting in your chemistry classroom, there's a high probability of finding you within like 100-meter radius around your chemistry classroom. But at any moment, you might be doing other things. Maybe you went to the bathroom. Maybe you actually weren't there that day and you were outside of that radius. You were sick, or you couldn't come to class for some reason. So I know typically where I can probably find you at any given moment, but I am not really totally sure. You could be in a different area. I have no way of knowing. I mean, I technically do, but you get the idea. So that's the idea, is that we created these this way of representing where the location of an electron could be in terms of probability. And that's what we call an orbital. So for the S sublevel, there's these s orbitals that are actually in spherical shape. Okay, so here's an actual little bit more of an accurate depiction. So that's what's called an electron cloud of an s orbital. And you can see it kind of forms this like spherical shape, right? And you've got these different axes. You've got your x-axis going from left to right. You've got your y-axis kind of sticking out at the page at you. And then you've got your z-axis going straight up and down. Okay, so the s orbitals are shown as spheres. And the sizes of those s orbitals actually increase as electrons have higher energy levels. So an electron in a 1s orbital is depicted, or I'm sorry, the 1s orbital is depicted as a smaller orbital than the 3s orbital. Okay, p orbitals. And I know this concept is kind of weird, you guys, just stick with me. So for p orbitals, we actually have 3 of them. There are 3 p orbitals. And we start at n equals 2. So what do I mean by that? Notice that at n equals 1, at the first energy level, we actually only have an s orbital. Okay? And each of these boxes represents an orbital. So you'll notice at n equals 2, we've got 1 s and 3 p orbitals. Okay? Okay, so a p orbital, we have 3 of them, and a p orbital has 2 lobes, and they kind of look like this. So I'll do my best to draw these. And you have 3 of them, so I'm going to draw 3. But each of these is a p orbital. So this is a p orbital. This is a p orbital, and this is a p orbital. Okay? And remember, what are these orbitals representing? They're representing the location that an electron is likely to be. Okay, so we're very likely to find an electron in these areas here. Okay, in these little lobes. And probably more likely to find them in the lobes than in the middle here. Notice how that's a very small volume there. We've got big volumes on the outer edges and smaller volumes in the middle. And we actually have a special name for the middle section there, but we won't talk about it in this class. You'll learn that later. Okay, so we're very likely to find electrons in those in those lobe regions, in those high volume regions. okay? And each p orbital can hold a maximum of 2 electrons. And we'll talk about s orbitals can also only hold a maximum of 2 electrons. In fact, every orbital can only hold a max of 2 electrons. So I kind of wish they didn't put that in this specific slide, but that's okay. All right, and then the 3p orbitals are arranged perpendicular to each other along the x, y, and z axes. So remember, you can draw it like this. Here's your y, right? I'm drawing it the way that we're used to seeing it, where we've got kind of like the x and y in the, you could call it in the plane of the paper. In the XY plane is what we call it. And then your Z is kind of popping out at you, like popping towards you. I'm not great at drawing in 3D, but this would be your Z. And it's perpendicular, okay? So this is kind of like sticking up at you, okay? Sticking out of the page. So the p orbitals actually arrange themselves or are arranged along each of those axes. So what do I mean by that? So here's a picture. This is just the combined p orbitals around the nucleus. But you can kind of ignore that for now because I really what I want you to focus on is the fact that there are 3 p orbitals and that they are oriented like so. So this p orbital is oriented along the x-axis here. Right? We can see that we've got our x there labeled. So that's, so we call that a px. And there's a 2 in front of that y. Yeah, because we're in energy level 2. That's the lowest energy p orbitals. Remember, because we don't have any p orbitals in the n equals 1 in the first energy level. We only have them in the second. Or we start having them in the second. And then the third has them as well, and the fourth, and so on. So we call that a 2px because it's in the x, what is that called? Axis. It's along the x-axis. Then our 2py, the p orbital that is on the y-axis is our 2py. Still 2 because we're still on that second energy level. Okay, and then the 2pz is along what axis? Yeah, the z. And it's still a 2, still a p orbital. It's got that dumbbell shape. So you need to know what these orbitals look like. Not this. Not this. Don't worry about that for now. You do need to know what this one looks like, these 3 p orbitals, right? And that they align themselves on different axes, but you don't necessarily need to memorize this guy here. That's a little complicated for our purposes. And then the S, of course, I do also want you to memorize your S's. Those are a little easier, right? Because they're just a sphere. They're easier to draw, I should say. Okay? All right, then you get a little bit crazier, and you get your D sublevel, and they contain 5 d orbitals. So remember, what's the sublevel? The sublevel is your, let me erase some of this here, is your S, your P's, your D, and your F. What are the orbitals? Those are those boxes, okay? So your D has 5 orbitals, 5 d orbitals in your D sublevel. And each of those orbitals can hold how many electrons? Yeah, 2. Each orbital can hold a max of 2e minus electrons. That is how I'll abbreviate electrons. So I'll write that out for you here, but in the future, just know that anytime I write E minus, I'm talking about electrons. Okay? What are the orbitals? Those are these boxes, right? Remember, your P sublevel has 3 p orbitals. Your D sublevel has 5 d orbitals, and so on. Okay, keep going. So you do not need to know how to draw these d orbitals yet. You will draw all of these in Gen Chem. And I actually urge you to draw them. Well, you don't need to do it now, but it is really fun. I think it's pretty fun, and it really helped me learn some of my 3D, learn how to think in 3D. That was not intuitive for me. Okay, so the D sublevels contain 5 D orbitals, and they look like this. They're kind of in like a little flower shape. They almost look like you took 2 P orbitals and like stacked them on top of each other. And the D orbitals, the first 4 here, they orient themselves in different orientations around different axes. We're not going to go into that too much, but you can kind of like predict it. So the DXY is on the XY plane, okay? The DYZ is lying on the YZ plane. The DXZ is lying on the XZ plane. This one's kind of strange, but it's like x squared minus y squared. And then you got this weird one with this almost like, looks like a p orbital, but it's not. Inside a donut. Kind of makes me hungry for a donut. Again, you don't need to know how to draw these. We're really only going to work with S and P orbitals in our class, but it is important to know in the future. And I do want you to know that they exist, okay, and that there are 5 of them. All right, so orbital capacity and electron spin. So there's something called the Pauli exclusion principle. And this states that each orbital can hold a maximum of 2 electrons. Okay, we talked about that a little bit before. Each orbital, remember those are those boxes. So I'll maybe put box, right? Electrons in the same orbital repel each other. Remember, if you've got 2 negative charges next to each other, they're going to want to get as far away from each other as they can. They don't like being next to the same charge. And then electrons in the same orbital must have their magnetic spins cancel, or must spin in opposite directions. What the heck does that mean? So it turns out that electrons actually, an electron actually spins on its axis, which generates a magnetic field. So when 2 electrons are in the same orbital, they repel each other unless their magnetic fields cancel each other out, unless they're spinning in opposite directions. When they're spinning in opposite directions, they create that magnetic field, and that cancels out that repulsion. It makes it so they actually will stick together. So this is kind of a depiction of how those electrons are spinning. So one is spinning clockwise, the other is spinning counterclockwise. They have opposite spins. You'll also hear something like spin up, and I'm trying to think of a way to, I guess I'll put spin up, and then I don't want to draw any more arrows because I don't want to confuse you. Spin down. Okay, I'm going to draw an arrow just for a second, just so I can show you. Spin down is referring to this arrow here, the downwards arrow, and spin up is referring to the upwards arrow. Okay, and that is just depicting that they have opposite spins. Okay, and you have one electron that's spin up and one that's spin down. So this is actually how we depict electrons in an orbital. So the orbital part of this picture here is the box, and this is kind of jumping ahead a little bit. And the arrows in there are actually representing electrons. So there are 2 electrons in this box, which is representing the orbital. Okay, and those electrons are oriented spin up and spin down. Okay, so the number of electrons in sublevels. Like we said, the max number of electrons in each orbital is 2, and there's a max number of electrons because of that can fill each sublevel. So the S sublevel has only 1 orbital. So how many electrons can that orbital hold? 2. So the S sublevel as a whole can only hold 2 electrons. Okay. What about the P? The P sublevel has 3 orbitals. Remember, you've got your 3 P's like this. and then here's your S. Each of those orbitals, right, these are each orbitals, can hold 2 electrons. So then you can hold a max of 6 in that sublevel. Okay, so I should say 2 here too. And then for your D sublevel, we have 5 orbitals. I'm not going to draw them out. I'll just draw them as like little boxes. Little boxes. What's that from? Oh, that's from that show. Okay, so 1, 2, 3, 4, 5. 5 orbitals, right? And each of those orbitals can hold 2 electrons. So 2, 2, 2, 2, 2. And 2 times 5 is 10. So that's where we get this max 10. The F sublevel, we didn't talk about a whole lot, but there are 7 orbitals in the S sublevel. So 1, 2, 3, 4, 5, 6, 7. Is that 7? Yes. And each of those can hold 2. 2 times 7 equals 14 total electrons, and that's where we're getting that number from. Okay? Again, the most important for our purposes is this section here, the S and the P. But I do want you to know the other facts on this slide. Okay? All right. Okay, so let's do this quick learning check and then I'm going to let you go because I know it's been a long video. So indicate the type and number of orbitals in each of the following energy levels or sublevels. So N equals 1, is that an energy level or a sublevel? That's an energy level, right? And then B is 3p sublevel. So now we are including sublevels. Pause the video, try it out, see what you think. Okay. So for N equals 1, the N equals 1 energy level contains one 1s orbital. Why do we have a 1 in front? Whoops. Why do we have a 1 in front there? Yeah, because we're in N equals 1 energy level. So that's what that 1 in front stands for. It's showing me the energy level. So let's write that down. Energy level. And then S is our orbital. Okay. Yeah, okay. Sorry, I got distracted for a second. All right, and then our 3p sublevel contains 3p orbitals, right? Why is there 3 here? What energy level are we? Yeah, we're 3, energy level 3. And then we have 3 of those p orbitals. So the type of orbital is a p orbital. So you could also depict that with your boxes. And you can draw in your electrons if you want. So I have 1, 2, 3, 4, 5, 6, 1, 2. Oh, I'm actually drawing those like this. That's another way. So up above we saw something like this, right? With electrons in spin up and spin down position. You can also draw them with half arrows like that. And that's just a faster way of drawing them, okay? Than drawing like the full arrows. You can do either one. I do think it's more efficient to just do it like this. So that's what I do. They're like half arrows. Okay. All right. So I don't want to go into 4.7 quite yet because this has been a long video. So I'll meet you back here for the next.